うん。というわけで、久しぶりですが、勉強を始めます。今日、プログラミング A、メールですね。Welcome to the first real module of the course. We know it is large and may therefore be intimidating at first. Everything is carefully ordered to build up a foundation one step at a time. Thus, the language, environment, and terminology are likely new to you. That's why you are taking this first week may feel particularly disorienting. All party of the course is the same environment. So, while here the module certainly
広告貢献1くらい、高弘さんが300プトニコに広告しました。
ごくありがとうございます。今日は ML という関数型言語の勉強ですね。Because the instant material from week 1 doesn't have a real homework and because week 3 requires getting used to so many new things, we recommend you start with week 2 material before then. で今回2週目から本格的に勉強が始まりますという。This was the purpose you start with any very simple program. What will likely look strange to you? Nothing but variables, numbers, conditionals. 変数とか数字とか if みたいなものにしかない。We focus on scope and shadowing before building on these concepts with functions. We then use pairs and lists and the two complementary ways to build a component on one data. Next, we consider left followed by next, including nested functions. They important of bindings efficiently. We finish with a couple of other specific language features used in our functions and booleans. And then since some more general perspective on the benefits running with mutation and different aspects of a programming language. 今までのプログラミング言語と全く違うよと。まずはペアとリストについて。ペア。Overall, that is a lot specifications also good terms are not intended to make sense before going through the lectures. So please work through the material methodology carefully. Timing things is likely to cause more grief than time savings. Our goal is to build a perspective and terminology that will allow us to build carefully, relentlessly, and efficiently toward a rich set of concepts that you intended and crucial for the upcoming modules. You will need most of all the videos to get the homework mark. It helps to understand functions, pairs, lists, and the let expressions before we can write very many intelligent programs. So do lectures first, trying out of your own by of the code presented videos, doing the video quizzes, otherwise making sure you understand what's going on. とにかく、フィードバックビデオや何かを見てしっかり自分で覚えろと。Then approach the program assignments, which divided into 11 separate problems. They are interrelated, so based on 11個の問題をチェックしてくださいと。In addition to the video and homework, as in the course module, there are other resources. The top of the module are reading notes that go. Same material as that lectures as well as download exercise and other in the videos. Bottom of the module show practice problem hints. The other resource contributed by このビデオだけこれで全部ダウンロードできると。 学習コンセプトリーディングノーツ。PDF でこういうのやってますと。プログラミングランゲージ2に ML のバリアブルバインディング。ここら辺をビデオでやりますということね。とりあえずビデオ見てみよう。ビデオ Our first program. Some errors. Errors fixed. Shadowing function. Suppose list. これ全部入ってるよねっていう。あ、まずはここにいろいろするレクチャーを見ながらやってみようと。ML のバリアブルバインディング。
Alright, without much further ado, let's get started with programming in ML. What I really hope you'll do as we start doing this is let go of any programming or any programming language you already know. For now, treat ML as this totally new thing. If you prefer, don't even call it programming. We'll have plenty of time later to compare and contrast what we're going to do in ML to things that you already know. And I really think that if right now you try to take each thing that I write down and say, oh, that's kind of like this thing I know in Java or in Python or in whatever, it's going to confuse you and make things more difficult. So it may seem like I'm going really slowly, but focus on the words and the terms and how we're thinking about stuff rather than trying to guess what the answer is going to be as we go. All right? So I'll usually have things open for us in advance, but since this is the first time I'm showing this to you, what I'm going to do now is open the Emacs editor. So this is what it looks like right after I open it. Your colors may be different. I've chosen these colors because I think they'll record better. And in fact, I'm going to switch the size here as well so that
Emacs を使っているところはこれのね。
Now I'm just going to open any file I want. I'll usually have this pre-done, but again, I hit Control X, Control F. And now I'm just passing in a path name. This file doesn't actually exist yet, first.sml.
Emacs から XF でファイルを読み込んで、
hit return, and now I have this blank file here. By the way, another simple thing you can do is if you create the file ahead of time, you can literally take your mouse, at least under Windows, and drag the file onto Emacs and it will open. So here I am in a blank file, and the first thing I'll do is write a comment. So this is a comment. This is our first program. So comments, like in every programming language I'm familiar with, are just things that are ignored by anything except humans. And in standard ML, we start our comments with a round parenthesis and then a star, and we end them with a star and then a round parenthesis.
ラウンドっていうのは丸書くことね。
So that's just a comment. We haven't written any program yet. Let's write a one-line program. Val x equals 34. This program is going to create a variable and is going to have that variable hold 34. And because 34 is something of type int, short for the English word integer, x will be a variable of type int.
なるほど。
Okay.
やってみましょう。今回のこれって。違う。学習用ビデオレクチャーの一回止めて、Windows ターミナルを起動したら、エデュケーションノーツのCouseraのニューワシントンプログラムテープ。 はい。まずはここに、コードで、デルタジオコードの方でいるかな。ウィークにノーツの新しいファイル。ファーストで、デメール。さて、拡張機能でバッシュバッシュバッシュ。バッシュはまあ、ほっといて、コモンリスプは、とりあえずもう、ビット。オカムルもとりあえず、で、リーバンスに、なったのか。デルチェックを、ナイムラって直径。こうにして有効のワークスペースと。そうすると、これでファースト、ネームの SML ね。ドットの、あの、これは、SML 動くから、オープニング、ユーズ。ならユーズなんだけど、R の、これで実行。オレディランニングだって。トップして、フェイズ3、RX の軸、X がイントになります。プリントとかできるか。ねえ。うん。アンダーズだよね。それで、その、じゃあ、でもいいか、ストップ。で、ターミナルの方を起動すれば、ウィーク、ウィーク、インのノーツと、SML のファースト SML であれば、意味だ。X 0ならば、取ると。では、続き。
See here is we are creating a new variable using the val keyword. So val is a special word in the language that says I'm about to introduce a variable. X is the variable name we chose. We could have chosen any
変数を宣言して、それに34を代入す
like
る。
y or foo or hello or Dan. Equals is part of the syntax of declaring a variable. And then here, between the equals and the semicolon to end it, I've put an expression. And the simplest kind of expression we have is just an integer constant. So let me do a second one. Let's create a variable y that has value 17. All right. Now I'm going to save with Control X, Control S. And now this is a program. I didn't need a main, I didn't need a class, I didn't need a method. For today, for this video, a program is just a sequence of these variable bindings. So each of these is a binding, we have a sequence of them, and that's our program. If I want to run this program,
代入というかバインディングなのね。
standard ML REPL, the read eval print loop. We'll talk more about that in a couple videos, but for now, let me just give you the basics of how you run this program. So I'm going to type Control C, Control S, then hit return.
SML
And
モ
that
ード。
brings up this other window where I can now say use and then first.sml. So the name of my file inside of quotation marks to make it a string. This
これで
function will
first.sml を
finish
読み込むっていう
command
意味だ。
use, then a semicolon, and then hit return. And sure enough, I get a message that it's opening that file, and it tells me some things. It says that it's created a value x, a variable x, that contains 34 and has type int, a variable y that contains 17 and has type int, and then this last line you'll always see, this is actually the result of running use, and you're free to ignore it. So I can now continue. I could add more things to my file, but I can also just use this prompt to see things. So if I type x semicolon, it'll say, oh,
まあ、
34.
X を入れたから X を見る
If
こ
I
と
said
できる。
x plus 7 semicolon, it'll say, oh, that's 41 and it has type int.
まあ、インターピーターだから
If
そのままできるってこ
I
と
forget the semicolon, it'll wait for me to continue some longer command. And so I can end it with semicolon, or I could have split things onto multiple lines and maybe added y to that and then semicolon, and that would be 58, and so on. We'll have more to say about the REPL in a bit, but for this video, what I want to do is just go back and continue writing our program and understand the exact meaning of what it means to have a sequence of bindings. So the nice thing about this sequence is that you can use earlier things in the sequence. So if I have x plus y plus y plus 2, now what will happen is when I go to create the variable binding for z, it will be able to use the earlier bindings. Now an obvious question would be, can you use later bindings?
式として入る
The
のか
answer is
な。
you cannot, and that might seem very strange or unusual, but it has certain advantages that we'll talk about in a couple videos. But the rule, every programming language has different rules, is that you can only use the earlier bindings. And the reason is that we can actually keep track of exactly what our program means as we go along. So I'm going to do this in comments, but this is exactly what the implementation of the language is doing when it sees all this code. So initially, we don't have anything. Now, it turns out we have a bunch of predefined functions and variables, but we haven't defined anything yet. And now after we create this variable binding x, what we have is what we have, I'll call a dynamic environment. It's the environment you have when you're running the program. And in that environment, let's say x holds 34. All right? And then after the next one, we'll have a dynamic environment where x holds 34 and y holds 17. And that's why when we get to this third one, we still have x holds 34 and y holds 17. And so what happens is we get to this expression and we evaluate
式をそのまま内にするのか。
current
変えるって
dynamic
ことなんだろ
environment.
うな。
So when you have an addition expression, you go and evaluate the two subpieces. So in this addition expression, the two subpieces, when you get a variable, you look it up in the environment. So we look up x, we get 34. We look up y, we get 17. Together, that's 51. Over here, we'll end up looking up y again. That will give us 17. Add two more, that's 19. And if my math is correct, we'll get, what, about 70 here. So z will, in this environment, now map to 70. And this is how we continue as we evaluate our program. So if next we had z plus 1, then I'm just going to paste this down. We'd have everything we did have in our environment, and now w holds 71.
ダブル式は違うけど、まあ、これもまあ
Happens
愛嬌だ
before
な。
any of this, and that is that our entire program, our file, our sequence of bindings is type checked. ML is a language with a type system, and if your program makes inconsistent assumptions about what's an int or tries to use a variable that's not defined, you get an error before you ever tried to run the program. And that is taken care of by what I'll call the static environment. Even though I'm showing this to you second, this all happens before the program is ever evaluated, before it's ever run. So what actually happened is the implementation first went through this whole program and said, oh, because 34 is an int, I know that.
型については固定なんですね。
X will have type int. It will hold something of type int. And similarly, as I go back through this
定
sequence, I
的
say,
な
oh,
環
well,
境
x
で
has type int,
今のよう
y
にイン
has
トが
type
入る。
int.
How to guess the type of z in the context? 当然イントになるってことやね。
All right. And here, now this is more interesting. The only reason that z gets to also have type int is because when I looked at this expression, when the type checker looked at this expression, it said, well, addition has type int if both the sub-expressions on the two sides have type int. Similarly, this addition can have type int if x and y have type int. And when you get a variable, you type check it by looking it up in the static environment. So the static environment acts a lot like the dynamic environment, except it just deals with what's an int or what's defined or what's not. And so it doesn't actually run the program. All right? So what really happens when you take this file is first everything type checks, then if that passes, everything runs. Now it may not look that way. If I flip over to my REPL here, and I'm always going to restart before I show you something after I've changed the file, it looks like it just figured out all together that x is a 34 and has type int, y is 17 is type int. But I really like to think of the type checking as coming before the evaluation. All right, let me show you a couple more kinds of expressions, and then we'll wrap up this segment. First, let me show you a conditional. So here, let me finish writing it out, and then I'll walk you through what's going on here. So I'm just creating another variable. This one's
マイナ
called
スって言ったら
abs of
z
z.
を作んなきゃいけないってこと。
And it says if z is less than 0, then 0 minus z, else z. And as you might imagine, the way an if expression is evaluated is different than addition. It doesn't go and evaluate all the sub-expressions. It first looks at this first sub-expression, z less than 0. It looks up z in the
まあ、基本
dynamic
的に if
environment,
then
gets
else は
70,
使えるけ
takes
ど、
0, asks less than,
参考変数
checks
みたいに考えろって
false.
言ったのかな。
So as a result, it ignores this expression between then and else, never evaluates it, and instead evaluates just the thing after the else, gets a result, in this case 70, and so the result of the entire thing, this if, will be 70, and we'll end up, therefore, putting the result as the value for abs of z, which is shorthand for the absolute value of z. So in fact, in our dynamic environment here, we'll have everything we had before, and then that abs of z maps to 70. As for the type checking, the way we type check an if then else is the thing between the if and the then has to be something of type bool, and indeed less than returns a bool, short for boolean, given two integer arguments.
あ
And
あ、
then these two
別
branches
ね、こういう
can
の
have
は
any type they want, but they have to have the same type. In this
if の
case,
場合、ボル
fortunately, they both have type int, and so the result of the entire if expression is type int, which is why abs of z in our static environment indeed has type int, as does everything else we've added to our static environment in this first file. And by the way, you know, this is a real programming language with lots of built-in features like less than and plus and minus. We didn't actually have to do it that way. There's a function defined for us called
ABS
abs,
っていう
which
関
takes
数
an
が
int and
組み込められ
returns
てる
its
ってことか。
absolute value. This is the first time I'm showing you calling a function. You might be used to something like this, and you can write it that way, but the parentheses don't actually matter. You can leave them out, and this would have
なん
done
か
the same.
省略できると。やっぱりテストが 12%、if 20の現状で。例えば、would you have industry test? まあ、これは int。まあ、ここが int で、if 文がブールの if になるってこと。
Okay, so that's our first program. Let me now get rid of this and just give you a little more sense of how the slides will work after I show you the code. So here's basically the program we just wrote. I like to include it in the slides, so if you're looking through the slides, you don't have to flip back and forth.
コードで書くと、バルイコール、バルイコール、バル、イコール、 プラス y プラスか y。割る u イコール z プラス a オーブン z 0 点 l 0まで説明ってこれでできるかどうか試してる。ある abs オーバー zd や。組み込みは abs を使える。ここまでやる。3番目のコンストラクターは y。ここ y が大文字だからね。じゃあ、これで use あー、右にはい。それで、エクスプレスの全体マイナス。0引く0ってないとダメか。これやっちゃう。ちゃんと0引く z にしてやると、z でかなり。じゃあ、これバル x イコールセミコンできるかな。それで、z70、ちゃんと普通に k 前の x になると。例えば、マイナス9セミコロンとできるか。無理。0引く9。マイナス1イコールマイナス70。x プラス z。エキスとセミコロンで出るかな。ダメだ。コントロール Z で抜けると。ということで、普通に ABC が実行できたと。では続き。
But we already saw all this. What we focus on here were variable bindings. And in general, the way we have a variable binding is we write val, the name of the variable, the equal sign, an expression, which I'm representing here in the middle of the slide with an E, and then a semicolon.
いいというのはエクスプレッションだな、適当だな。
Syntax. Syntax is how you write something down. I haven't said what it means. That we talked about with the code, and I have it here on the last slide of this little segment, and that's the semantics. So syntax is how you write something, semantics is what that something means. And we're dividing our semantics into type checking, which is what we do before the program runs to make sure there's nothing inconsistent.
型チェックが入って、それぞれの変数に型が結びつかれる。それについて計算が行われているがダイナミック。
You type check the expression, that E after the equals, and use that to extend the static environment. When you evaluate the expression, that ends up extending the dynamic environment. So that's this meaning of variable bindings, but it seems clear that the meaning is going to depend on what kind of expression we have. So for each kind of expression, variables, additions, conditionals, less than, they're going to have their own syntax, type checking rules, and evaluation rules. And to go through those, you can go to the next video.
高い人。一応、ちょっとやってきてるの忘れてたんだな。 うなった駅、例えば、val x イコール 34.5 セミコロンとすると、リアルになるんだ。じゃあ、レッド x イコール8はセミコロン。ダメだ。これ後でやれ。一応、リアルと型が入って数値が入るってことね。
All right, in this segment, we're going to take the same program we had in our previous segment, and we're going to look at those different kinds of expressions we saw more carefully and make sure we give them a precise semantics so we know exactly what they mean. So we're going to take the same program we had before. You see it here on the PowerPoint slide. And we're going to really focus in on those expressions that we had for each of the variables that we bound. We're not doing this because I think you don't understand addition or what an integer is or how a conditional expression works, but because by giving the semantics to these things very carefully, we'll be able to build on top of that and use this exact same ideas when we learn more sophisticated and interesting language constructs in the near future. So if we look at this program, we see a bunch of different kinds of expressions, either explicitly in the program, like 34 or a variable x or an addition, as well as a couple things that we don't see in the program but would be the result of evaluating some of those expressions, like the Boolean constants true and false. So in fact, I thought I would show those to you quickly. If here's my program, and I can go ahead and open the REPL here, there really is a constant true. Just like there's a constant 42, and that's the result of things like conditional expressions. So 3 less than 0 evaluates false. And if I include those variables that I bound, then I can use those in less than expressions as well, and I can ask is x less than y? Turns out it's false, but if I ask is y less than x, that evaluates to true. So we have these kinds of expressions as you might expect. But we also have this neat property that we can build expressions as big as we want. So certain expressions like addition, less than, and conditionals are built out of smaller sub-expressions, and that can nest as deep as you want. So you can have an addition inside of another addition, you can have a conditional inside of an addition, you can have an addition inside of conditionals, and that can go as deep as you want, making expressions as big as we want. So when we go to define the syntax and semantics of expressions, that definition is going to have to be recursive because we're going to have to define it in terms of those sub-expressions. So there's a really important methodology to what we're going to do right now, and that is for every kind of expression to ask ourselves the same 3 questions. What is the syntax, i.e. how do you write it down? What are the typing checking rules? In other words, what type does an expression have, and what could cause it to fail to type check, in which case you get an error message. And then the third question is, what are the evaluation rules? Assuming it does type check, how does it perform its computation in order to produce a result? And we're going to call that result a value. Of course, expressions might not produce a result. They can also raise an exception at runtime or go into an infinite loop.
さて、select the 3 things we want to think about for experience. Syntax, how will you done its calculation? この4書き方をするか。Valid types. First type was allowed type. Evaluation, how will you valid type? どのような方々が式の評価。How will you done? そうだな。ターミネーションのこの場合は出力コードっていうか、
Okay, so let's start with the simplest kind of expression I can think of, which is a variable. So we're going to ask 3 questions. What is the syntax? The answer is it's any sequence of letters or digits or underscores, except the first thing in that sequence can't be a digit. The rules for variables in ML are pretty similar to what they are in many programming languages. The second question is, what are the type checking rules? This is when we're using a variable, not when we're defining it with a variable binding, but when we're using it as an expression or as part of a larger expression. So the answer is, the way you type check a variable is you look it up in the static environment. If you find it, whatever type it has in the static environment, that's the type of the expression. And if you don't find it, it doesn't type check, and you get an error message. And then the third question was, what is the evaluation rules? Here it's similar to the type checking rules, except we look the variable up in the dynamic environment and we use whatever value we find there. We don't have to worry about it not being there because in ML we only run programs that type check, so we know that variable will be in the dynamic environment. All right, so that's variables. Like I said, they're pretty simple, maybe even a little too simple. So let's next do addition expressions. And these are our first example where the expression has sub-expressions inside of it. So the answers to all of our questions are going to have to rely on the answers to the questions for the sub-expressions. So first, what's the syntax of an addition expression? It's any expression where you have two other expressions with a plus symbol in between them. That means you have an addition expression. Okay, so what are the type checking rules? Well, what you have to do, given an addition expression, is you have to type check both of those sub-expressions, E1 and E2. And if they both have type int, then the addition expression has type int. If either of them does not type check or has a type other than int, then
まあ、
the
完
entire
全に
thing
数学的
is
定
not
義の
type
話になっ
checked.
ちゃうな。
See how the answer for the larger expression is built out of the answers for the smaller expressions.
Both insist that E1 has type int and E has type bool. Then what is type int? It doesn't type. こうなるんじゃないかな、多分。だってデビットそうだし。Addition is not defined the addition into the bool. So this expression will not type check. Does not type. つまり数プラスブーリアンみたいなことをやると、型が合わないので、それのタイプはつかない。どうなんだろうな、エバリュエーションは。つまり、ML、O プラス、アルスとかやると、あ、エラー出た。インとかけるブルーなので、それは形で合わないことはできないと。例は出ないよと。
And similarly for our evaluation rules, we're going to take those two sub-expressions, E1 and E2, evaluate them to values. Let's call them V1 and V2, whatever they might be. And then our overall result will be the sum of V1 and V2. And again, thanks to type checking, I know V1 and V2 will be ints, so I know that it will always be possible to sum them. All right, so that's addition. We all knew how addition worked. Now, before I get to the more interesting one, which is conditional expressions, let me talk a little bit more about these values. So remember, the result of evaluating something is a value. So it turns out that every value is an expression, but not every expression is a value. So what we have are these certain kinds of expressions, the values, that are always going to evaluate to themselves.
マイナスの数字が入ってないんだよ
42
な。
evaluates to 42. True evaluates to true. There's actually even one, the result of that use command we use in the REPL produces this value left parenthesis, right parenthesis that has type unit. So for each of these types, there's a certain set of values, and those are the answers that we get when we have some expression of that type. So we know how 34 works. Its syntax is a sequence of digits. Its typing rule is that it has type int. And its evaluation rule is that it's a value, and like all values, it produces itself as its answer. Okay, so those are the values. Now let's do a more sophisticated one, which are the conditional expressions. And I thought it would be more interesting to write this out rather than just already have it up on the slide. And since my typing is much better than my handwriting, I thought I would just open a text file in Emacs and write it there. So the syntax for a conditional expression is if E1, then E2, else E3, where if, then, and else are keywords, or the actual syntax that explains what this is, what construct this is, and E1, E2, and E3 are sub-expressions. So the same way an addition has two sub-expressions, a conditional has three sub-expressions.
Moving on to type checking. What type must E1 have in its S? E1 はブールじゃなきゃいけなくて、This special type doesn't いつでいつも見たらいけないんだよな。なんでってことああ、もう一回、プールには行けないってことか。いや、トゥルーかファルスで言ってなきゃいけないから、ブルーがあると。
Now, the type checking is more interesting and is different than with addition expressions. So first, E1 must have type bool. It must be true or false, or a variable type bool, or a comparison, or some expression of type bool. E2 and E3 can have any type. Let's call it T, but they must have the same type.
同じタイプである必要はあるが、
So you can't have a then branch of one
それは
type
どれ
and
でもい
then
い。
branch of another type
つまり、
because the result of our entire
今のところ
expression
イン
might
と
be
しかやって
either
な
of
いけ
them.
ど、
And what we need is
リアルと
the
かそういう
type
のもいいって
of
こと
the
か。
entire expression is also T. And last, we have the evaluation rules. In here, we first evaluate E1 to a value, call it V1. Since it type checked with type bool, I actually know that V1 will be true or false. If it's true, evaluate E2, and that result is the whole expression's result. Else, evaluate E3, and that result is the whole expression's result. And that is everything there is to know about the
定義を言ってるけ
syntax,
ど、まあ要する
checking
に、
rules, and evaluation rules of
E1 の定義
unification.
にトゥルーだったらいい。
So, to finish up, let's have you do one, which is to figure out what it is for less than comparisons. Try to work through it on your own, just on a blank piece of paper. If you get stuck, it's also in the reading notes associated with the lecture, and then we can ask some questions about it as well. So remember, for all of these, the details are less important than the fact that we always ask the same question. How do I write it down, the syntax? What are the type checking rules? And then what are the evaluation rules?
この3つが基本と。REPA。じゃあどういう時に REPA ってのがあ
All
る
right,
か。
in this segment, I want to take a brief break from building up our conceptual framework for understanding ML to go through a couple more pragmatic topics, namely how to use the REPL, that read eval print loop, effectively, as well as how to deal with error messages and show you a bunch of examples of errors that are fairly common when starting to learn ML. Okay, so we want to ask a couple questions. First of all is how do we run programs using the REPL, and what does it mean to have a REPL? And then what happens when we make mistakes, and how can we go about debugging those mistakes? And fundamentally, debugging is a skill you develop over time, and I just want to give you some practice with it by watching me do some. So the way we've been using our REPL was primarily with this use expression. And really the way I want you to think about it is that it takes the contents of a file, and it's like you typed in those bindings, those variable bindings, one at a time into the REPL. And that really is what happens. So if I take this file, which we've seen before, it has a bunch of bindings. When I come over here with Control-C, Control-S, return to bring this up,
SM 入れ
I
る起動し
could
て、
manually type these in one at a time. Val x equals 34, val y equals 17, and so on. But instead, when I say use first.sml, it does that, but all at once in a batch, showing me the result of doing all of those bindings, what are their types, and what's the result of evaluating them. And that's all that it's doing, and it's convenient that way. And so when you look at it this way, what is actually going on is the meaning of our programs is that all we have is a REPL, and use is just a
レップ
convenient
ルは
way to use
リー
that.
ド、エバル、プリントル。
So REPL stands for read eval print loop, and it's actually pretty well named. That what happens at that prompt when you type in a binding is it reads it, it evaluates it, although if it doesn't type check, it just gives you an error message to that extent. It prints the result, and then the loop part is about how it gives you another prompt back so that you can continue. So we can just think of this as a strange way to run programs where we open up the REPL and then we type use, but it's often quite convenient for after you type use to then go ahead and try a few things out. Now, after you type use, you find yourself typing the same thing over and over again, like you're building up a collection of test cases for, say, your homework problems. You're probably not making an efficient use of your time. And it's better to go ahead and move those tests into a second file, and then go ahead and use one file, then use a second file that's going to include all your tests, and then maybe do a little extra playing around. But what I don't ever recommend, for reasons we'll discuss in the next segment, is typing use, playing around, and then using the same file again. Instead, what you'll always see me do is come over here to the REPL, type Control-D to end my session, Control-C, Control-S, return to restart it, and then it's okay to type use again with a file. The REPL won't stop you from doing it another way, but I don't recommend it because it's often very confusing what's going on. Okay, so now let's turn to errors. Usually when I show you programs here in the video, they just
そういう
work
時にエラー
to
が起きる
demonstrate
か。
something, but we all make mistakes. You can make a syntactic mistake. You don't write something down the way you expected. You can make a type checking mistake. What you wrote down is the correct syntax, but it doesn't follow the type checking rules for the language construct you're using. Or it might type check and then run, and either it produces an exception, or it goes into an infinite loop, or it produces an answer, a value, but not the value you wanted. So debugging has to attack all of these problems, and one of the hard things is you often don't know which mistake you made, and the error message you get from ML may not help either. And there's a few reasons for that. Well, the good reason is, well, you wrote something that isn't what you intended. So whatever error message you get is just ML's best guess as to what might be the problem. But it's up to you to figure out what actually the problem is. And the other thing is that as much as I love ML as a language and love having a read eval print loop, the error messages you get, particularly when you have a type checking error, are usually actually quite bad. And it's really a bit of an acquired skill to look behind them and figure out what you did wrong.
Which one of these errors is not consistent tracking in ML? Is semantic mistake. あとは確実にエラーが出るよねってことだな。A。シンタックスエラーしろってことをもう一回やってみよう。Which one of these errors not concern? 無理ではない。Debugging usable. エラー。Binary compatibility? これが確実ではない。
So the best way to learn something is by trying it, and I want you to just try writing ML programs. Don't be afraid of errors. Slow down, find what line number the error is coming from, and so forth. And I thought I would help point you in the right
まあ、
direction
エラーは
by
出る
just
から
doing
そ
a
の
little
こと
bit more
で
myself. So
い
I
させるんじゃ
have
ない
a
っていう。
second file here that is called errors.sml. And it looks like a pretty good program here. It turns out it has a bunch of errors. And this
まあ、
is
わ
the
ざと
entire
作っ
thing.
て、エラーが出る
Suppose
や
I
つを作
wrote
っ
all
たよ
this
ってやつだ
down.
な。
And now I go over here and I say use errors.sml. Okay? So
14
it
行
turns
の
out
1エラー、
it
選択で
includes a
やっ
couple
て
errors
LCID。
here. The first one you can see is at line 14, and it says syntax error inserting else ID. Okay, so if I go over to line 14, which you can see here in Emacs down at the bottom, it prints out the line number. That line is just val a equals minus 5. So it's not, you can't look at that line and figure out
マイナス5っていうのは使えない。
It turns out is often the case, well, the error is actually a little bit before the line number that's being reported as the problem. And indeed, if you look up here, I have this if-then expression. Well, in ML, there's no such thing as an if-then expression. You need an else afterwards, which it thought you might want to put on line 14. I actually want to put it up here. And I have to have else something. How about else 42? And that's because, as we know, when you have a conditional expression,
セミコン抜けてるんやな。
either branch, the then or the else, might need to be evaluated, so you can't leave the else off like you can in some programming languages. So, okay, we fixed that error. Let's go back here, come down to the end, restart things, try again. And by the way, if you don't want to keep typing this, you can type meta p to get your previous commands back. And now we see an error on line 18. It says replacing fun
ジャンプできないのか
with
な。
wild. Now, if you look at line 18 here, it might look just fine to you. Why can't I have a
フ
variable?
ァンっていうのは予約だから
Well,
使え
as
ないってこ
often
とね。
happens when you're learning a programming language, we stumbled across a keyword. It turns out fun means something else in the language, and we're not allowed to use it for a variable. So we're going to have to change this. And how about funny? That should do the trick. Quit, restart, type that back in. And now we get a whole bunch of error messages. They don't even fit on the screen because we now don't have any syntax errors that ML found. So it's giving a bunch of different type errors. And I like to fix the first
Unbound
one and then
variable
come back.
constructor
So
X.
up here on line
Unbound
8,
variable
it says
constructor X. X
unbound
と
variable or constructor X. So if I look at line 8, sure enough, I am using X
バルが
here, y
家
equals
の
x
X
plus
が
1,
入ったの。
but it sure looks like it should be bound. It should be in my dynamic environment from the previous line. But it turns out that the error here actually is syntax, even though it looks like type checking, because I'm not actually finished with the previous expression. If you want to start another expression, you have to type val again. Since I left that off, the type checker thought this entire thing was one expression, and for
X
this
イコール
expression,
34
there
抜け
is
る
no
形
x
の
in
y
the
イコール
dynamic
をその
environment
まま
yet, because I
評
haven't
価しようとする。
finished
あ
defining it. So I have to put val here. By the way, I used to put semicolons at the end here, and you still can. You have to in the REPL, but in a file, it's
バルが
not
な
actually
あるから、
necessary.
見こな
It
った方
turns
が
out
安全って
that
こと。
was not the error, but leaving off the val was. So, all right. So we'll try this again. And we still have a bunch more errors, but at least now we're up to line 10, where it says test expression in if is not of type bool. If we go over here to line 10, aha, it actually got one right. This is actually a very accurate error message.
y だ
Right
けでは
here, this
計算が続けないからちゃん
y
と
has type int, because that's the type of the variable y, and you're not allowed to have something of type int there.
この厳
You
密
have
に
to
やん
have
なきゃいけ
something
な
of
いか
type
ら、
bool. So this is just nonsense code, but maybe
y
the
大なり0と
programmer
やっ
meant to
て、
write if
実に
y
ブ
is
ールに
greater
な
than
るようにす
0.
る。
Okay, so we fix that one.
まだエラー
Go
出るは
back
ずだな。
here, restart, try it again. Still a bunch of errors. Still on line 10. Types of if branches do not agree. We remember that the then branch and the else branch both have to have the same type so that that can be the type of the entire if then else
34と X の
expression.
4合ってる
And
から、
indeed,
例えばここ
34
が
is
例えば
type
トルー
int,
とか
and
7に
just
行っ
less
た
than
んだ
4 is
な。
type bool. So I don't know which of these is wrong, but I have to fix one of them. How about fixing that one?
なるほどね。
All right, back
両
we
方ブーリアンなら
go.
問題なし。
Hopefully you don't usually make this many errors in this few lines of code. But we're up to line 14. Expression or pattern begins with infix identifier minus. Oh, this one might not make you very happy at all. It's actually
マイ
complaining
ナ
about
ス
the
5っていうの
minus
は定義
5.
できないから、
Maybe that seems crazy to you, but in ML, the only thing you can use minus for is as a binary operation, like x minus 5, or 0 minus 5, or 13 minus 5, or so on. If you
き
want
と
to
し
write
て
a
マイナス
zero
5やったら
number, you
ザ
might
ル
say,
空
oh,
転
well,
できない
0
ってことだ
minus
な。
5 would work. You don't have to do it that way. There's just different syntax in ML. When you learn a programming language, you have to learn that
入れ
language's
てもいいような
syntax
気もするけど
rules.
な。
It turns out that negation of one argument is the tilde character, with or without a space here,
ティルダ
not the minus character. You can't use minus, you have to use
ティル
tilde.
ダはどこまでもなるわけか。Where is that ティルダ key on your keyboard? Don't come on your keyboard. キーボード見てくれてくれ。待って。
And that
という
will
こ
fix
と
this one.
は、エラーズ後でやることにしていいけど、SML、ティルダをセミコロンとやると、IT イコールティルダを、じゃあ0を引くとセミコロンとやる。X、じゃあ X イコール0マイナス6セミコロンで、はいはいはいはい。X イコールティルダ6。ティルダとして表示される。なので、ティルダを使えと。
Problem. And we're up to line 20.
これは確認するためだけど
Operator
も。
and operand don't agree. Real star real, int star int. The expression it's complaining about is this x/w, where presumably I was trying to do a division.
X。
Well, that is
0 で
a
デバインするとき
division
は、
of
0 を
floating
リアル
point
としてエラー
numbers
出る
in。ML, which it calls reals, but it doesn't apply to integers. You're not allowed to use slash on integers in ML. That's just the type checking rule. But there is a different operator for division, and it's spelled div for div. All right, so we maybe looked
エ
that
ラー
up
ゼロし
somewhere,
よ
and we've got that fixed, and now we can run this, and that looks like a very different kind of message. So it turns out we're not getting a type checking error here at all. We're now actually everything type checked and we're running the program, but when we run it, we got an uncaught exception for divide by zero. Like in many languages, you get an error if you divide by zero when you run the program. It's not a typing error. And sure enough, if you look at this xdiv w, when we go to evaluate w, we look it up in the dynamic environment, and we get 0. So if we don't want that error, we're going to have to do some different division. How about dividing by w plus 1?
So
let's go back here one more time. And look at that. We actually ran. We have a bunch of types now. We have a bunch of values. But if you look at the end, not this val it, that's the result of the use itself. But the last
14 イコール0とか嫌なパターンではあるな。
variable 14, and it is bound to the value 0 of type int. Now that's not necessarily a problem, but maybe it's not what I meant. And I brought this up, I included this just to remind you that sometimes you get this great sense of satisfaction when it all type checks, it all runs, but you still have to make sure you have the right answer. And if I wanted this to be 14, I probably didn't want 7 minus 7, I wanted 7 plus 7. Of course, there's no way a type checker or an automatic tool can know what I meant. 14 is just an English word. But you still have to test your program and look at the answers and make sure it all works.
そういう意味論的なところがやっぱ見えないよね。
Finally happy with what I've got, and so let's stop there.
シャドーイング。シャドーイングとファンクションまでかな。これ毎日やんね。いや。これやれっていうことならちゃんと学習用教材。for some errors。読め、ダウンロードできるかな？大丈夫かな？ some error。あ、ブロックされた。じゃあ、これは Firefox で開いて、全部読んでいいようにする。そうすると some errors が、普通に開いちゃう。リンクを、ニューブロックオリジンで、クラウド、これ、ファースト、E マトリックス。じゃあ、こう全部送って、our first ダウンロード系、エラーズもダウンロード。エラーフィックでダウンロード。シャドーイングと、ファンクションもダウンロードしましょう。で、ここら辺を、エデュケーションの、あれ遅い。プレフィックスの、これを消して、このエラーフィックス。 このサムエラー。このシャドウ。ファンクション。これを、ワークス。5と。一回閉じてみる。どうかな。ピーク2のノーツのエラーです。ダッシュ、オーバー、ダメか。マックス、ピーク2つ、ノーツで、マックス、5のダメエラーです。よいしょ。これをやるには、シルバーフォアです。で、やるべきか。ダメか。なのに、ここで使おう。で、閉じて、エラードフィックやってやつだな。サムエラーズ X。これをランすると、エラーが出る。ターミナルで SML を起動して、ーズ、オーバー、ダメだ。サムエラーズ。ナビゲットファイルアトリビュース。ほんでなし。じゃあ一回閉じて、SML。この、そっか。SML、ウィーク2のノーツのオーバーサムエラーで SML。これでエラーが出る。じゃあ CD ウィークリーのノーツとして、SML ロスからできるけど、ユーズ、オーバーサムエラーのエラーは、14行1 S ナテ SDA、IDA。14行セミコロンにして、例えばこうすれば、エルダーとしてすれば、12行インサーティングレッド。 inserting let else 8とかすればいいのかな。だった。8の上、4倍バルのコンストラクター X。ここにバルを入れれば、いつかく、そこに、こうなってるから、例えば、ブルーにすれば、y、ダッシュ、コール、0。これでどうだ？エクスプレッションコントロール、S とセーブして、こうすると、10の14行10。アンバウンドバルのダッシュイコール。大なり、小なり0。収めてみますが、リプレイシングファンをいつファイル。ファンをやっぱ使えないので、ファンにする。これどうだ？ in expression 0。リアルイン。x プラス w。これが w で、プラス。いやいやいや。距離は0なのが悪いのか。0とかいいのかな？ 0.1。これで、リアルインで。うん。じゃあ w をイントの1にすれば、プレートオープンのノンドゥの w で、by ミスマッチ。ウェル&ドメインにプラン。つまり、ここを div にすればいい。おう。v イコール0だ。14イコール0はおかしいから、こう最後に7プラス7にする。よーし。こんなもんでどうでしゃろう感じですね。これで今日は1時間、もうちょっと行きましょう。あ、なるほど。とすると、プログラミングのタイプ A の今2週目をやってるから、シャドーイングを再開と。
Okay, in this segment, I want to talk about shadowing. Shadowing is when you add a variable to an environment when before you added it, that variable was already in the environment. So to do this, we're going to end up having multiple variable bindings for the same variable in the same file. That can be a little bit confusing. It's usually poor style to do that, although it does come up with certain idioms. But it's going to be a great way to make sure that we really understand how environments work. So I'm not going to give you any new rules. There's no new syntax, no new type checking or evaluation rules here. We're just going to use this idea of shadowing to really explain how environments and variable bindings work so that we have that solid foundation we need when we go to add things to the language. So let's just start here by adding this binding val
A
equals
イコー
10
ル
to our
10
environment.
で、
And so we know now
これ
that
は
in
A
a static
がインテジ
environment,
ャー
A will
の
have type
数値
int,
がナンバ
and
ーに
in a
なると。
dynamic environment, A will be bound to the value 10. And so, of course, if we then continued in our file with a times 2, b would have the value 20. I'm going to ignore the static environment here just for expediency, but of course that's relevant as well. So now the interesting thing happens if we say val a equals 5. All right?
これさっ
The
きやっ
thing
た。
I really want to
A は
emphasize
5になって
is
B は
that
A イコール2やけど20もあったん
b
だよ
is
な。
still bound to 20. And in fact, if I next said val c equals b, even though right here I had an environment where a maps to 5 and b maps to
ああ、なるほど。
20, now I have an environment where a maps to 5, b maps to 20, and c maps to 20. Because
まあ、
you
それは
know
普通だ
that
な。
the way you evaluate this expression b is you look it up in the dynamic environment, you get 20, then you extend the dynamic environment so that now c maps to that result. All right, so the fact that b was earlier created by evaluating a times 2 is no longer relevant. That was back in an environment where a mapped to
結果が
10.
計算
We
し
got
て
20.
20が入っ
We
てる。
extended our environment so that indeed a mapped to 10 and b mapped to 20. And that's the end of the story. The fact that we had a times 2 is no longer relevant. And I should emphasize as well that this val equal 5, this is not an assignment statement. Okay? There is absolutely no way in ML to mutate or change the fact that A
あ、
mapped
そ
to
っ
10
か。
in the previous environment. All we get is in the subsequent environment, A is now shadowed. We have a different mapping for A in a different environment, and A is now 5. So that's the idea. Let's just do a little more example to make sure we got it. If I now say val d equals A, I'm going to end up with an environment with all the things I did have, and now d maps to 5 because a maps to 5 in this environment where I am. If I now say, what about val a equals a plus 1? Again, there's no such thing as an assignment.
ああ、そっ
And this
か。
makes
代入じゃないん
perfect
だ。
sense. The way a variable
全
binding
部
works
イ
is
ミュー
we
タブルだか
evaluate the
ら、
expression in the current
新
dynamic
し
environment.
く
So a
領
maps
域
to
を割り当て
5,
て、それの数
we
値入るわ
add
け
1
ね。
to that, we get 6, and then we create a new dynamic environment where a maps to 6, along with everything else we had previously, but we're now shadowing the fact that a mapped to 5 in an earlier environment, or a mapped to 10 in an even earlier environment.
スタンダード ML
So
ニュージャ
indeed,
ー
if
ジ
we
ーだ
now say
か
val
ら、
equals a times 2, f
4にな
will
るわけね。
map to 12. I should emphasize as well that something you cannot do is a forward reference. And we know why for the same reason. So if I had this code here, it would not
え
type check. And the reason
え
why
これ
is
は
if
ス
I
タ
had
ンダード
not
ML で
checked,
す。
this expression f-3
ML
is
の
not yet in the
正統
environment.
派
So when I look it
の
up
関
in
数
the
型言語
environment,
で
it's
すね。
not there, and I would get a type error message. So that's the example I wanted to show. Let's real quick try it out, make sure I typed in everything correctly.
Use shadowing ですね。今のファイルをセミコロンで実行すると、
Let's, there we go. We'll try this again. Notice I didn't panic when I got an error message. There
セ
we
ミコロン
go.
できると
And
カメ
we
ラと
see
か使っ
all
て
the
たりと
values I
か、
saw. But for those earlier A's, the read eval print loop is trying to be helpful and just saying, you know, this value can't possibly be relevant to you. I know it's shadowed in the dynamic environment you now have down here, where A is bound to 6. So rather than show you what A was back up in this earlier environment, I'll just print hidden value. All right, so
ああ、
that's
そういう
the
ことか。
code example. Let's go back to the slides here.
新しく値を入れると、前の値をシャドーイングされるってこと
In the
か。
key example here, when you have something like val equal a equals 1, b equals a equals 2, that in the environment you end up with, b is bound to 1 and a is bound to 2. There's actually two reasons for this, either one of which would be enough. The first reason is that we evaluated that expression we used for b, that expression a on the right-hand side of the equals, eagerly. Back when we evaluated the variable
すでに
binding
計
for
算
b.
された後
So
だか
after
ら
we've、done that expression
前の値に
evaluation,
ついては関係
b
ない。
is bound to 1, and it doesn't matter how we got that 1. It'll never affect the fact that we got a 1, and that's the end of the story. The second reason b will stay bound to 1 is that that second val equal 2 is not an assignment statement. The earlier a, the a that leads to the environment that is used to evaluate b, is still 1. All we did was create a second variable b that shadows it.
つまり、これ X の12が、これシャドウされる。Multiple is bound to the variable A after the following code is speak. X イコールにこれ X になります。X が12、N イコール14、X イコール0。N イコール X で8。だって、B が、ここか。X になって0になるのかな。違う。いこう。これは、こういうのはコピーして、コードで実行した方がいい。さてな。新しい。第5じゃない。うん。ET は邪魔だけど、続きしましょう。X イコール2割る N。ちゃんと読んだからダメだな。1行ずつ割る N イコール2プラス。ダメだ。value N イコール2プラス X。で、value X は N-14。で、計算して、0になる。すると、それを計算すると、N は N×X。とりあえずここまでで、こうしてみると、X2X00 となる。B コフ N9.8 L ス5。バルーン B は N イコール X。ならば、なるはずで。そうじゃなければ、こう。バリュー A イコール if B イコール5で X。else B。これを実行するから、これで A と B が8になる。で、続
So it turns out this is the reason I'm so insistent on not having use commands in your REPL more than once for the same file. Because if you say use multiple times for the
Use as
same
best.
file, you're going to repeat whatever bindings were there the first time you said use for the file and are still there the second time you said use for the file. And while it's legal in ML to have that sort of shadowing and to reintroduce those bindings, it can be really confusing, right? Maybe you took a binding out, but it's still there because of the previous
ゲーム
use.
バインディング
Or
ス、
maybe
同じよう
you
な
do
値
some
を設
shadowing that
定
makes
す
it
る
look
け
like
ど、
your code is
あれと
correct
は
when
違
in
う。
fact it's wrong because of how the shadowing happened to work for the multiple use statements.
なるほど。やる前に、今のやつを例をやって、ファンクション。基本だ。
Okay, in this segment, we're going to start studying functions. These are a new kind of binding. So we're going to change our program, definition of program, to not just be a sequence of variable bindings, but to allow both variables and functions. If you haven't heard of the term function, it's a lot like a method in an object-oriented language. This is something that's going to take arguments,
X の0、
some result,
液状を
and
求
return
め
that
る
result.
件数。
That's all it does, so it's in many ways simpler than a method, and we're always going to call these things functions. So why don't I just flip over to Emacs here and show you a first example. How about I write a little function for exponentiation or raising something to the power of something else. So here is most
型
of
を
what I
こ
need
うつけるようにな
to
ってる
write.
のね。
Okay, so I have the keyword fun, the name of the function I'm defining, pow, the arguments it takes, here x and y separated by commas. I've written their types with a colon and then the type name, then an equals, and then I have my function body. Okay, so that body can just be any expression I want, and what happens when you call the function is we are going to evaluate that expression, and then the result will be the result of the
これ
function.
式をそのまま
So
定義すればいいの
for
か。
exponentiation, what I want is something like a conditional expression that says if y is 0, then 1. Otherwise, how about x times this other expression, which is to call the
X
pow
の方が
function
低い。
with x and y minus 1. And that will
おお、
work
典型的
as
な
long
末尾再起。
as y is greater
ル
than
ー
or
プをし
equal
なくて
to
再
0.
起が使え
And
た
I'll make no attempt to be correct for negative y, since this is just an example.
ファンクション per x の y equal x. What would happen if y is negative? こう言えばいいじゃないの。y イコールなんですかね。途中でエラーが出て遅い気がするけど、そうだよね。
So this is a program. This can be included in my sequence of bindings. I could have a val binding before. Maybe afterwards, I could have another function binding. How about something that takes its argument and cubes it? So I could define this as x
Cube
times x
equal-
times x. Or I could use any previous
もう
binding
やっ
since
た
I'll be in my environment. And I
パ
could
ウ
instead implement this as pow x3.
液状水を
So
す
the
る。
body of this cube function is itself a function call that calls pow with x, which is the argument to cube, and the constant 3. All right, so I could use these functions. I could say val 64, that should just equal cube of 4. Then I could maybe use parentheses, but it looks a little more like other languages if I put them in, at least for now. Or I could have something that uses more nested expressions, like you can call a function
2の6
with
乗、
an
2の4
expression,
乗か。
in which case I'll evaluate this 2 plus 2 to 4 and then pass 4 as the second argument to pow. Here I could add another
4の2乗。
16 and another 8.
2の3乗。
You could even have nested calls if you wanted, so you could say pow 2, 2.
ああ、確かにそうなるけどさ。
When you want to test something out, just like always, go over here to the REPL. We can say use functions.sml. See all of our bindings there. You'll notice that pow and cube print differently than variable bindings. In terms of the value, they just say, I'm a function. We don't print out the body of the function or anything. The rep will always just say, here is a function, and here is its type. So you see with POW that it has type int star int arrow int. So the way function
関
types
数
are written
は
in
ファンク
ML,
ション
we
で、
write down the type
係
of
数
the
がイントとイン
arguments
ト。
separated
結果イン
by
トは
a
もう
star.
バインディング。
So it takes two int arguments, int star int, and then a hyphen and angle bracket and arrow, and then the result type, which is an int. Notice we didn't have to write down that result type. ML figured it out by looking at the function body, that conditional that we had up here, and realizing that if x and y have type int, the conditional has the type int, and so the function, when called with two ints, will return an int. Similarly, cube is a function that takes one int and returns one int. 64 and 42 are as usual, and we can, try things out at the REPL now.
当
We
然
could
キューブ
cube
で
7,
7 を
and we would get 343.
7を計算す
So
る。
that's the informal idea of functions. Let me make a few points here back with the slides, since this is a new thing we're learning. The first thing is that the body of the POW function itself can use POW. So that's how we implement recursive algorithms, as we did here. So all this is showing is that inside a function body, you can call the function itself.
Gotcha. Previously, we talked about leaving our parents when calling functions. Note that here, we've always been using parents called the POW function. Which of the following is the legal way to call POW? When calling function, note that there, we've always been using parents called the POW function. Which of the following is not the legal ね。ちょっとこれ全部正しいから、これが間違う。正しい。やってみろと。なので、ファンクションに入ってるから、今のを、これができる。ターミナルの、use 7は、ファンクを読んでみろと。パウエッタ。そうすると、R ANS を歴上を2個括弧はセミコロンだけ。ベースをつけると、出た。じゃあ、バル、コンセプト、ベースの2個も。エラーが出た。それでもなんだじゃあ、X をそういう風にタップルにして宣言できるんだ。バル ANS つまり、正しい、だってのこれなんだ。これが間違ってる。そう。Answer function has exactly one argument. Units use parentheses to call it. 関数一つのアーギュメントしか持ってない。つまり、二つのアーギュメントというわけじゃなくて、括弧2,3っていう一つの 指数を持ってそれを計算してるってことなのね。わお。
There's a few gotchas when you start writing things out. We have all new sources of potential error messages, especially if you leave that colon off between the name of the variable and the type, or if, like in other languages, you try to write int x instead of x colon int.
意外と
All of
基礎
these
的
things
な
are
間違いするん
syntax
だ
errors,
な。
and you're going to get error messages as a result. I would also point out that when we wrote out those function types in the REPL, we saw that POW had type int star int arrow int. That star is different than the star for multiplication. So it's just a reuse of the same character. In expressions, star means multiply. In types, at least as we've seen so far, it's just separating the types of multiple arguments. And finally, just like variable bindings, function bindings can use earlier bindings in the file, but they can't use later bindings in the file. And that's, again, just ML's rule. So any helper functions you want, if you want to define one function like cube in terms of another function like POW, then you have to put cube second. Now this does raise an interesting question. What if you had 2 or 3 functions that all wanted to call each other? There would be no good order to put them in. And I'll show you in some future segments some special support in ML for that case of mutual recursion. If you're not yet comfortable with recursion, hopefully you've at least seen it before. You will be soon. On your first homework assignment, pretty much every function you write will be recursive, and we're going to see a bunch more examples. So don't panic if the algorithm for POW looked a little too magical. But there's really absolutely nothing magical to it. So let me flip back here and just show you this POW function. The reason why we can define POW in terms of POW, there's nothing circular here. What we did is we defined raising something to the wife power in terms of raising something to the y minus 1th power. And that is a perfectly reasonable definition. Our recursive call is solving a simpler problem, and if that simpler problem is that y is 0, then we don't use recursion at all, and we just return the answer 1.
まあ、再起だから、そっぱり条件に0が必要だろう。
And in ML, we're always going to use recursion for these sorts of things. If you're used to writing things like POW with while loops or for loops, we're not going to use them. They often obscure what are simpler, more elegant algorithms, and recursion is more powerful. So often while loops and for loops are more convenient, or the idiom in many programming languages. In many programming languages, they're more efficient. But anything you can do with a loop, I promise you, you can do with recursion, and we're going to focus on that approach in ML and really most of the...
さて、ファンクションについての正式な定義。
In our last segment, we learned how to define functions, like the functions POW and cube that you see here that we wrote. And we learned how to call functions, like you see at the bottom with cube of 4, and you see in the bodies of cube, where we called POW, and in POW, where we called POW. So we got a sense of how to write these things, but I want to take a more formal look, because one of the things I'm trying to teach you is how to give precise understanding to what constructs of programming language mean. So let's just jump in and look first at that function binding. When you define a function, what's the syntax? What are the type checking rules?
で始まり、関数名 x0 が入り、
Syntax in general is the
x0 の
keyword
でいいね気が
fun,
するな。
FUN, then a variable, which will be the name of the function, then the list of arguments, which for now will have be variable name, colon, type, separated by commas, inside parentheses, then the equal character, and then an expression, any expression you want, as deeply nested as you want, with all sorts of sub-expressions, and that E is what we call the function body. Let me do evaluation rules next, because this is so simple it may seem strange. A function is already a value. When we have a function binding, we add x0 to our dynamic environment so that later expressions can call that function, and that's all we do. We don't evaluate that function body until we call the function, and that's a different language construct we'll do next. So, takeaway message, a function is already a value. All right? Type checking is not as simple. So let's think about how this works. All right? The end result of type checking a function body, so we're going to take that function name called x0 here on the slide, and we're going to add it to the static environment with the type, takes arguments t1, t2, t3 up to tn, and returns a t, And you see the function syntax here with t1 star, separated arguments by star, and then an arrow by t.
これ、引数型がいくつかあると、その型を見て、
And here's how we type check that function body. Basically, we type check E using everything that was already in the static environment, because E can use any earlier bindings. And it gets to use the arguments, so it knows x1 has type t1, x2 has type t2, and so on. And since we allowed functions to be recursive, x0 can be used in E. It is in the static environment, and it has the type of the function overall. Okay? That last one might seem a little bit magical, since the type checker has to figure out the type of x0, but we'll learn later in the course that it's not so magical. It's just one of the neat things that ML can do that for us. All right, so let's go into a little bit more detail on the type checking here. So we do have this new kind of type, t1 star for all the arguments, then the arrow and the t. So that's the result type of the function over on the right. The overall type checking result is to give x0 this type. And those arguments, x1 and x2, those variable names, those are not added to the static environment for after this binding.
これはやってるしかないな。
Static environment for the body of the function. That's probably not too surprising. That's how methods work in Java, or functions or methods in Python or anything else. Those arguments are only in scope, or only in the static environment for E, not for the code after this function definition. Okay? Next, because the evaluation of a call to x0 is going to return the result of E, that type that is the return type for the function, t, is the type that E has. So what the type checker does is it type checks E, it gets some type, and then that's the return type for x0. And as I already mentioned, this is a little bit magical since we never wrote down t. The type checker is just able to figure it out, and we'll have to discuss later in the course how it's able to figure it out.
When a function definition is encountered, the body of the function is evaluated. にゃ false unless the function is defined. こういうことだよね。電気評価、その時にこれら先に評価されるから。
Okay, so those are function bindings, how we define functions. It turns out we added another construct to our language, and that's calling a function, using it. And those function calls also have a syntax, type checking, and evaluation rules. So let's go through those. When we had a function call, let me show you in the code.
全部式として呼ばれる。
pow x y minus 1, or here's another function call, or here's one, or here's one. There's a couple more. All right. The way we always wrote those is with one expression, which is what function we want to call, and then some other expressions in parentheses and separated by commas, and those are the arguments we're calling the function with.
Notice that the XML there isn't a way to have functions that take variables in number of arguments.
So when we had something like pow of 2 and 2 plus 2, the first expression, pow, will look that up in the dynamic environment to get
これはパウっていう
function.
関数式を呼び
And
出
then
す。
these other arguments we'll evaluate, and those will be the arguments of the function.
かっこいい
But
式
that's
がま
getting
ない。
ahead to evaluation rules. Syntactically, it's just expression and then more expressions in parentheses separated by commas. You don't need the parentheses if there's exactly one argument, but if there's 0 or 2 or 3 or 4, then you do. That's the syntax. Type checking, how do you type check a function call? Well, rule number 1, E0 better have a function type. it better have a type that has that arrow in the middle with the arguments on the left and the result on the right. Assuming it does, then we type check all of the other expressions, E1 up through En. There better be the right number of them for the function that we're calling, and each one better have the right type for the function that we're calling. And if that's all true, then the result of the function call is the result type of E0. So it would have type T, as indicated here on the slide. So that's why when we had something like pow of x comma y minus 1 in that recursive function, it ended up having type int. And let's see why here. Because we have this call here. So we look up pow, and pow itself has type
まあやってみたいよね。
star int arrow int. So fortunately, we're calling it with 2 arguments. And when we type check x, we look it up in the static environment, which here in the function body has type int. Then we have to type check y minus 1, which similarly will have type int, because we can look up y, and then subtraction takes 2 ints. So the call type checks, and then the result of the call will have type int, because that is indeed the result type.
イントが結果出るから、それがイントになる。
Okay, so that's type checking. Evaluation rules are also interesting for a function call. So here's what we do.
エバリエーション、式の評価が。
First, evaluate E0 to figure out what function you're going to call. So if you're going to call pow, you're going to look up pow in the dynamic environment. You're going to find the right function binding. Second, you're going to evaluate all of the arguments, E1 up through En. So you're going to get values. So when we had something over here like pow of 2 and 2
呼ぶとしたときに、それぞれの引数を計算して、式の値が入る。2プラス2でから結果の4が入れ入り、式の4として、ラインとして呼ぶさ。
It's going to have no idea how we got that 4 as the result of an addition. So that's step 2. And then step 3 is to actually evaluate the function body. Now, how are we going to evaluate that function body, like the body of pow? We're going to extend the dynamic environment that was there back when we defined the function with extra values for the arguments. So x will be 2 and y will be 4. In general, are the n arguments to our function, x1, x2, up through xn, end up with the being bound to the values for this call, the first value argument, the second value argument, the third value argument. And lastly, inside that function body, any recursive calls are bound to the function itself. And so that's why when we do something like call pow with 2 and 4, we end up evaluating this function body in a dynamic environment where x is bound to 2, y is bound to 4, and pow is bound to the function itself. So, as always, when we introduce a language construct, no matter how simple or how complicated, we can understand it completely with syntax, type checking rules, and evaluation rules. And that's functions.
回数のペアはキャンセルして、までで、シンプルなだけで時間かかるんだよな。今のうちにチェックしましょう。当然出るはず。ああ、やんねえよ。今のことでいい。例えば、当然、マイナス4とやると、ああ、とか。これで、今ではインターファースまで止まんない。2.0なら。じゃあ、例えば、ファンクションズのスクリプトじゃない。ファンクバウリアルy コロンイントってもできるはずなんだ。コール if y0 then 1.0 else x かける how x も y。これもできるはず。これで、use。ヒントされた。ということは、パウ4コンマ2は、エラーになるはず。4×4 だから 4.0 の2なら、になると。はい、了解。消し終わります。だいたいわかった。これで2時間なので、ちょうどいいところですかね。もうすぐ1時なので、今日はここまでにします。ではでは。明日は次がいけていい。